For the past couple years, I've been playing around with teaching AIs to play video games, and I figured why not start recording the process. For my first recorded project, I decided on a game from my childhood called Tetris Attack. This game really has nothing to do with Tetris. In fact, I can't believe I played it as a kid. I think it's just proof that if you slap Mario characters or anything, kids will play it. One of the more difficult parts of this project is the fact that it runs through an SNES emulator, meaning all the interactions that I have with the game have to occur through the emulator. And so this is going to prove pretty challenging later on, but let's jump right in. Now, before I can really code anything up, I'm going to need a way of getting information from the emulator. So, what I'm going to do is I'm going to open up Cheat Engine to extract some memory information from the game. This is going to allow us to get the score, the state of the board, the cursor position, and things like that I'm going to need to be able to train the AI. So, I start out by selecting the BSNES process, which is the emulator that I'm running this game on. So now I'm going to start searching for memory addresses. What I do is set the score in the game and search for that value in Cheat Engine. Cheat Engine will narrow down all the addresses which contain that current score. All these are possible memory addresses for the score, but I need to narrow it down by continually playing the game and checking for updated scores. As you can see, I've narrowed it down to two options. These are really neighboring memory, so they both contain the correct cell value. And as you can see, as I play the game, those values are going to change according to the score, meaning I've found the correct address. I now know this highlighted address is the offset I need to be able to read the correct memory value in Python. I went ahead and repeated this process for all the game state objects I would need, such as the score, the cursor position, the state of the game, whether the game is live, the chain count, and whether the clock is stopped. As you can see, those values are changing in Cheat Engine as I play the game. So now I can take all of those offsets I got using Cheat Engine and write some Python code to extract that data automatically. So now that that code is complete, you can see that the console is being spanned with information from the game. So we can successfully read in information from the emulator, but we have no way of sending output to that emulator, like keyboard commands. So that's what we have to do next. So now that that code is complete, we actually have a way of controlling the game. We can now automatically move the cursor and click the mouse, but this is certainly far from an artificial intelligence. We need to add some logic to the way that it performs moves. We're going to start out by using somewhat a brute force algorithm, which is able to calculate all the possible moves and board states and try to determine which move is the best from that state. This is just going to be the first stage of the AI. So while I speed through some of this programming, I'm going to explain how the algorithm actually works. Before the AI generates an action, it'll take a snapshot of the state of the game. Based on this state, it will generate a list of moves that are possible to take from this position. This list excludes moving tiles that are the same because that would accomplish nothing, but it also excludes some tiles that can't be moved, such as ones that are affected by gravity. After generating this list of moves, the algorithm wants to estimate how good each of these moves are. In order to do this, it simulates all of these moves and then simulates gravity that applies afterwards and tries to guess how many points it gets for making those moves. This is typically referred to as a fitness value, and right now I'm just writing my own arbitrary function to determine this fitness. The fitness function I created grades the game state based on how many points you got from combos and chains, but also penalize having a tall tower. I also use another metric called roughness, and this is just to determine how flat the game board is because I want to reward a flat game board. So now that I've finished the algorithm, let's try it out. Well, the algorithm is actually pretty good already, but I'd like to improve it just a bit more. Also, it isn't really an AI yet, so I want to add some AI. Currently, the algorithm makes decisions based on these get fitness and should raise functions I've implemented. Now, the most important part of this code is the section where I calculate the fitness, because this fitness is what determines the behavior of the search algorithm. Now, I basically just made this function up on the spot because it made sense to me, but it could be optimized. I could go in here and tweak these values until it performs better. I could even create a genetic algorithm to tweak the constants in this function. But instead, I'm just going to completely rewrite this using a neural network because it's more powerful and can find correlations between different parameters better. So, let's code it up. Luckily, I had planned on writing this piece since the beginning, so my code was already set up to add this pretty easily. All I had to do was create another agent which used a neural network to solve instead. Then I had to go ahead and write a script which would be used to train that neural network. And now we can start the training. So, right off the bat, in Generation 1, we see that most of the AIs just immediately lose the game by racking the towers all the way up to the top. But even in the first generation, by chance of just random values, it actually manages to get a decent score. We see a few of the AIs are able to score a couple points, I think just by clicking randomly. But that's the advantage of using this algorithm is it does most of the heavy lifting as long as you get the values for the parameters in a decent range. But later on, we're going to get a little more optimization. How this training works is that each generation has different agents with different values in the neural networks. They each get a chance to play, giving them up to 60 seconds of game time to rack up the highest score possible. The best of these generation are allowed to move on to the next generation and also breeding and mutating new children, and hopefully they will slowly improve over the generations. And so that was one of the major disadvantages to training on an emulator because all of this has to happen in real time and only one agent can play at once. So this training process actually takes a significant amount of time if you want to have many children per generation and run the simulation for many generations. And because this training took so long, I'm going to speed through some of this training process just to show you some of the best agents from each generation. It turns out, because of the assistance of the algorithm, I probably didn't need to train it for so long. It actually manages to converge on a good solution very early on in the generations. After the 11th generation, progress seemed to stall out a little bit, and it's partially due to the randomness that each generation receives as part of its training. Each board has more potential to score more points, and so each generation would start fresh with a different game board. However, it really was up to luck whether they could score a lot of points. It wasn't until Generation 23 where we started seeing a little bit more progress. Generation 23, there was an agent that was a little bit more comfortable allowing the board to build up more before starting to score points. This allowed more tiles to pile up to give it more potential to score more chains and combos. But after this, there really wasn't much more to learn. The agent had essentially capped out. I think I could have done more improving by adding more functionality to the algorithm. The AI is really limited to what the algorithm can do, and that's just a product of what I had to do in order to make this feasible to be trained on an emulator. There are definitely more improvements I could have made. One of the biggest problems is that the AI can't actually see into the future. It's only capable of estimating about one move in advance. Also, there are some optimizations I could have made and some improvements to the simulation algorithm I had. But overall, the AI performs pretty well, and I'm ready to move on to the next project. So I'll just end this video with some footage of the AI playing a pretty good game.